In this lesson, we will learn how to use a technique called integration by parts to antidifferentiate some additional functions. So first of all, here is the integration by parts formula. It says that the integral of u dv is equal to uv minus v du. So first of all, let's talk about what that means and where it comes from. So suppose you have two functions, uv, and you take their derivative. You use the product rule. So we will have u prime v plus u v prime. Now if we antidifferentiate both sides, we have the antiderivative of u v prime is equal to the antiderivative of u prime v plus the antiderivative of u v prime. Now the antiderivative of u v primed is going to be u v equals the antiderivative of u prime v plus the antiderivative of u v prime. Now if we isolate this, we have that the integral of u v prime is equal to u v minus the integral of u prime v. And how this connects to the above notation is this: instead of v prime you use dv, and instead of u prime you use du, and this formula becomes the integral of u dv is equal to uv minus the integral of v du. So this formula allows you to translate an integral of this form into something that you can maybe take care of. And let's do an example. Let's apply the integration by parts technique to evaluate the integral of x sine x. So first of all, the formula is the integral of u dv is equal to uv minus integral of v du. Usually you choose u to be something whose derivative disappears as you differentiate it repeatedly or becomes a constant. So we will let u equal x, then du is the derivative of that, which will be dx. Now dv is the other component in the integral, so we'll choose dv to equal sine x dx. And to figure out what v is, you have to antidifferentiate that, and the antiderivative of sine is negative cosine x. So the formula tells us that this integrand is the same thing as uv, so negative x cosine x, minus the integral of v du, so negative cosine x dx, so negative x cosine x, plus the integral of cosine x. Now this second integrand is something that we can actually find. So we have negative x cosine x, and antiderivative of cosine will be sine, plus c. And let's just verify that this actually worked by checking to see if the derivative of our solution gives us back what was inside the integrand. So apply the product rule to the first portions. The derivative there will be negative 1 cosine x minus x times negative sine x. The derivative of sine is cosine x. C's derivative is 0. Now the cosine x's cancel, and we just get x sine x as expected. Now let's try another one. Suppose we have x e to the x. Now once again the formula is the integral of u dv is equal to uv minus integral v du. So let's choose once again u to be equal to x, and then du will equal dx. If we let dv equal e to the negative x dx, to find v we have to antidifferentiate, and the antiderivative of e to the negative x will be negative e to the negative x. So this integral is equal to negative x e to the negative x minus the integral of v du So negative e to the negative x dx. So negative x e to the negative x plus the integral of e to the negative x. And once again, the second integrand has been reduced to something you can actually handle. So negative x e to the negative x. The antiderivative of e to the negative x is once again negative e to the negative x plus c. And if you want to verify that's correct, you can do so using differentiation. It's not very difficult. Now in this case, consider why this will not work. So if I let u equal y cubed, and I let dv equal ln y, you don't actually know how to anti-differentiate ln y. So that's not going to work. Let's try something different. It seems as if our only option in this case is to let u equal ln y and let dv equal y cubed dy. That will give us du is 1 over y dy, and v is the antiderivative of y cubed, which is 1/4 y to the 4th. So this integral will be equal to uv minus integral v du. So uv will be 1/4 y to the 4th ln y minus v du. So we'll pull up that 1/4. Integral 1 over y times y to the 4th dy. Now we can cancel a y, and that integrand becomes antiderivative of y to the 3rd, which you can do. So we have 1/4 y to the 4th times ln of y minus 1/4 times 1/4 y to the 4th plus c, or 1/4 y to the 4th ln y minus a 16th y to the 4th plus c. Alright, next we're going to find a formula for the antiderivative of ln x. You know a formula for differentiation of ln, but not antidifferentiation. And it seems like there aren't that many options here. So if you let u equal ln of x, du is 1 over x dx. And what else is left? Well, what's left is this dx. So if you let dv equal dx, then v will equal the antiderivative of 1, which is x. So then the antiderivative of ln will be equal to uv minus integral v du. So x ln x minus the antiderivative of x times 1 over x dx. And x times 1 over x is just 1, so I have x ln x minus the antiderivative of 1 dx. Well, and the antiderivative of 1 is just x, so x ln x minus x plus c. So that's the antiderivative of ln x. It is x ln x minus x. That's a formula that you can use, but this is where it comes from. Let's use that formula to find the antiderivative of ln of 3x plus 1. Make a u substitution and let u equal 3x plus 1. So then du is equal to 3 dx, or 1/3 du is equal to dx. So the integral of ln of 3x plus 1 is equal to 1/3 antiderivative ln u du. And apply the formula we learned in the last example. So we'll have 1/3 u ln of u minus u plus c. And then let's reinsert what u is, and we'll have 1/3 times 3x plus 1 ln of 3x plus 1 minus 3x plus 1 plus c. There are ways to simplify that sum, but for now, that's good enough. Now, sometimes this technique must be performed repeatedly to antidifferentiate a function. So here's an example. Let's let u equal t squared. Du will equal 2t dt. If we let dv equal e to the t dt, then v will equal e to the t. So the integral of t squared e to the t is equal to uv, so t squared e to the t, minus the integral of v du, so 2t e to the t dt. And the second integral still isn't something we can evaluate without using integration by parts, so we have to use parts again. And when we do that, we're going to let u equal t, du will equal dt, dv will equal e to the t dt, and v will equal e to the t. So then we'll have minus 2 times the quantity uv, so t e to the t, minus the integral of v du, so e to the t dt. And the antiderivative of e to the t is just e to the t, so we end up with t squared e to the t minus 2t e to the t plus 2 e to the t plus c. Now, because the power on t squared was 2, we had to do 2 iterations of this process. Had that been t cubed, there would have been 3 iterations of the process. T to the 4th, there are 4 iterations, and that would be cruel. But it is important to understand that you can repeat this process until you reduce the integral to something quite simple that you can use basic antidifferentiation rules to figure out what it is. Alright, a definite integral. So what I think was best here is let's just antidifferentiate inverse tangent of x, and then we'll go back and do the evaluation step later. So this is kind of similar to the ln example. We let u equal tan inverse of x, so du is 1 over 1 plus x squared dx. We let dv equal to dx, which means that v is equal to x. So the antiderivative of tan inverse is equal to uv minus integral v du, or x tan inverse x minus the integral of x over 1 plus x squared dx. Now this integral is something you can find using a u substitution, and we already used the variable u, so let's do something else called like w. Let's let w equal 1 plus x squared, so dw is equal to 2x dx, or 1/2 dw equals x dx. So we have that the antiderivative of tan inverse x is equal to x tan inverse x minus 1/2 the integral of 1 over u du, or x tan inverse x minus 1/2 ln 1 plus x squared plus c. But since we have a definite integral, we don't have to worry about the plus c. Now, evaluating from 0 to 1, so the area under the tan inverse curve from 0 to 1 is found by first plugging 1 into this expression. So 1 tan inverse of 1 minus 1/2 ln of 2, and then plugging in 0. 0 times tan inverse of 0 minus 1/2 ln of 1. And the second expression is 0. In the first portion, the inverse, tan inverse of 1 is saying when does tangent equal 1, so that's pi quarters minus 1/2 ln of 2. Now here is a rather tricky application of this integration by parts technique. So we're going to find the antiderivative of e to the x sine x dx, and none of the function sort of goes away as you differentiate it, so well, let's just give it a try. I'm going to let u equal sine x, and I will let dv equal e to the x dx. So now the derivative of sine is cosine. The antiderivative of e to the x is just e to the x. So the antiderivative of e to the x sine x is equal to uv, so e to the x sine x minus v du, so minus e to the x cosine x dx. Okay, and now we apply it again. And if you picked u to be the trig function in your first step, you must pick u to be the trig function in the next step also. So let's set u equal cosine x, du is equal to negative sine x dx. Once again, dv is equal to e to the x, and v is equal to e to the x. So I have that my original integral is equal to e to the x sine x minus the quantity uv, so e to the x cosine x minus the integral of negative e to the x sine x dx. Just be careful to keep good track of those negative signs. We have e to the x sine x minus e to the x cosine x, and eventually we'll have minus the integral of e to the x sine x dx. And you're back where you started. So what you do now is a very clever trick. You have that this is equal to that. What we're going to do is add a quantity e to the x sine x to both sides of my equation here. And that gives us twice the integral of e to the x sine x dx is equal to e to the x sine x minus e to the x cosine x. And now to find just the singular integral of e to the x sine x dx, we divide by 2, or multiply by 1/2. And the antiderivative of e to the x sine x dx is equal to 1/2 the quantity e to the x sine x minus e to the x cosine x plus c. That technique is sometimes called around the world, and it's a little strange, but you can combine like terms. That integral is a quantity of something, and you can add two of them together. So it's a pretty clever trick.